Good morning or good afternoon, everyone, and welcome to JavaCard Forum 4th webinar series or for 2024 webinar series. This is Jean-Daniel Roussel, President of the JavaCard Forum. Today's webinar is a talk on the role of cryptography in EMV, chip payment security, and it's given by Mike Ward of EMVCo and Pham Nguyen of Infineon. Michael is chair of the EMVCo Security Working Group, which supports and maintains the specifications and algorithms, and also guidelines related to security and long-term security requirements. Pham is JavaCard product definition engineer at Infineon and has been active in JavaCard and embedded software for over 20 years. Cryptography is key for ensuring the highest level of security of payment cards following the EMVCo specifications. In this webinar, Mike and Hugh will present how this is achieved, and in particular, the latest cryptographic technique based on elliptic curve cryptography. In addition, most of today's payment cards are developed on JavaCard platform, and Mike and Hugh will also present the ongoing collaboration between the JavaCard Forum and EMVCo to support emerging security protocols such as Blinded DiffieHellman or Elliptic Curve Schnorr digital signature. You will be able to post questions during the presentation in the chat window if you wish so, and we will open the microphone at the end of the presentation where you will be able to ask directly questions. Please also note that the presentation is recorded and you will be able to have the slides and review the presentation on our YouTube channel or directly from the JavaCard Forum website. Without any further delay, please welcome Mike and Hugh. Mike, Hugh, the screen is yours.
Thank you, Jean-Daniel. Thank you for the introduction. Yes, I'm Mike Ward, and on behalf of the EMVCo Security Working Group, I'm going to tell you all about the role of cryptography in EMV chip payment security. I'll then hand over to my colleague from the JavaCard Forum. So, this is the agenda for my part of the presentation. I'll begin with some background information on EMVCo, and then I'll describe the EMV chip security architecture in terms of how it uses symmetric cryptography for remote authentication of the card to its issuer, and how it uses public key cryptography for local authentication of the card to the terminal. I'll then get into some specifics of which algorithms are used for authentication. I'll divide these into old, by which I mean the ones used since the beginning of EMV 20 plus years ago, and new, by which I mean the ones introduced more recently. I'll conclude with a deeper dive into how cryptography is used in the new EMV contactless terminal application, known as Kernel 8. But before getting into the technical stuff, let's briefly talk about EMVCo. So EMVCo's mission is to facilitate card-based payments that work seamlessly and securely worldwide. We deliver on this mission by developing specifications and supporting approvals and evaluation programs for products that enable the delivery of consistent and convenient payments for merchants, businesses, and consumers around the world. Key to EMVCo's work is close collaboration with the payments industry to adapt and evolve these specifications so that they continue to support technology innovations, the needs of different marketplaces, and changes in consumer behavior. EMV specifications are technical requirements for designing payment products to work seamlessly and securely everywhere. This is important to the delivery of safe and reliable payments that merchants, businesses, and consumers expect globally. Over 100 banks, merchants, technology providers, and other industry stakeholders contribute to their knowledge and expertise to the development of these specifications. This results in EMV specifications being used across the payments industry to create products and services that deliver trusted and convenient payments for merchants and consumers around the world. So, this slide reflects the global adoption of EMV and the importance of the security that EMV provides. The card payments industry is moving to EMV chip, and this is clearly shown in these figures between 2021 and 2023. Looking at the bottom row of the table, You can see that it's a lot now and is still growing. I'll now describe at a relatively high level the security architecture for EMV chip transactions. So, a typical EMV transaction is where a consumer uses their payment card to buy something in a shop. So two necessary players in this transaction are the cardholder and the merchant. But the other critical players are their banks, the bank that issues the card to the cardholder and the acquirer bank that sponsors the merchant to accept payment transactions. And last but not least, there is the payment network that provides value-added communications between acquirer and issuer. And this includes the payment networks such as Amex, Discover, JCB, MasterCard, Union Pay, or Visa. Service providers may also be involved. During a payment transaction, the cardholder presents their card or mobile device to the merchant's terminal, and the terminal initiates a series of commands to the chip on the card, and the chip provides responses to the commands, culminating in purchase approval or decline, or what is most common nowadays, a request for the transaction to be sent online for approval by the issuer. Communications between chip and terminal is either contact, where the chip card is actually inserted or dipped into the terminal reader, or contactless, where the card is simply waved close to the terminal reader and communications uses NFC, near field communication. And of course, it is contactless communications that enable mobile phones to also be used as the consumer device instead of a plastic card. During a transaction, the card will, in response to an unpredictable challenge number from the terminal, create two types of cryptogram: an offline cryptogram that can be verified locally by the terminal, and an online cryptogram that can be verified remotely by the issuer. To avoid requiring that the card and terminal share secret keys, EMV uses public key cryptography for the local authentication. But because card and issuer can share secret keys, EMV defines the use of symmetric cryptography for remote authentication. I'll briefly describe each card authentication method in the next two slides. So EMV local authentication depends on a pre-established PKI, a public key infrastructure, where the payment system has a key pair, the root key of the PKI, as does each issuer bank. And the issuer public key is certified by the payment system. The issuer generates a key pair for each card, and the card public key is certified by the issuer. The card keys and certificates are provisioned into the card, and the payment system public key is distributed to the acquirers, and thence to the merchant terminals. Then at the time of the payment transaction, any merchant terminal possessing the payment system public key can, as part of local authentication, verify the certificate chain in order to authenticate the card's public key and the card itself. So for EMV remote authentication, this can instead use symmetric cryptography. The issuer can derive card master keys from its issuer master key using the card's account number as derivation data. Each card is then provisioned with its card master key before issuance to the cardholder. Later, during a payment transaction, the card derives a session key from its card master key using the card's transaction counter as derivation data, and then uses its session key to compute a MAC over transaction data that is sent to the issuer and can be verified by the issuer. Having provided an overview of the security architecture for EMV, we will now focus on the cryptographic algorithms used by EMV, and we'll do this in terms of old and new. By old, I mean the cryptography that was defined in EMV from the start 25 years ago, such as RSA and two-key triple DES, and that is still used by most EMV transactions today. And by new, I mean algorithms such as Elliptic Curve Cryptography and AES that have been included in the last 10 to 15 years and are not widely used yet by EMV transactions. I remark that the design of the new public key cryptography had its origins over a decade ago, when EMV was planning a new common specification for both contact and contactless. In the end, this initiative did not come to fruition, but the ideas for the cryptography did ultimately get added to the existing contact specifications in EMV Book 2 and to a new EMV contactless terminal application specification, so-called Kernel 8 as defined in the EMVC8 specification and EMV Book E. I'll begin by describing the old cryptography and the algorithms used for local authentication and remote authentication. Local authentication relies on public key certificates and a card digital signature generated using RSA and SHA-1 according to ISO IEC 9796-2. The card digital signature is of type DDA or CDA, depending on when in the transaction it happens and the amount of data authenticated by the signature. 2 points to note here are that the maximum RSA key size is 1984 bits due to the maximum size of the card response message, and that the algorithm is mandatory and EMV type approved so as to ensure global interoperability between cards and terminals that perform local authentication. Algorithms for remote authentication, on the other hand, are not mandated by EMV but simply recommended as their use is between the issuer and the issuer's cards. The old recommended algorithms are based on 2-key triple DES and 8-byte MACs, generated using the so-called retail MAC algorithm, standardized in ISO IEC 9797-1. I'll now describe the newer algorithms. The newer algorithms for local authentication use elliptic curve cryptography and the Schnorr variant of ECDH for digital signatures, as defined in ISO 14888-3, and using SHA-256 and NIST curve P256. Whereas contact transactions require the card to generate a digital signature known as XDA, similar in function to CDA, for contactless transactions, the card and terminal instead establish a secure channel using a blinded form of DiffieHellman, standardized in ISO 11770-3. And the card generates a secure channel MAC called EDA MAC using the AES CMAC algorithm. And I'll talk more about this later. For remote authentication, it is anticipated that issuers will use AES and CMAC, because these cryptographic functions will anyway be implemented on contactless cards for the local authentication. That said, for EMV, the actual algorithm used for remote authentication is simply recommended, not mandated. I'll now describe in more detail the cryptography defined by the new EMV contactless terminal application called Kernel 8. I'll start though with an overview of the security objectives and an illustration of the blinding of DiffieHellman key agreement. The security objective is to have a secure channel established between card and reader that provides authentication to the terminal of card and card data, and communications integrity, including a protocol to detect relay attacks, the so-called RRP, a protocol to help detect and thereby prevent relay attacks. Just as a reminder, a relay attack is typically where a fraudster makes a transaction at a legitimate merchant by relaying in real time the merchant terminal communications to a card of an unsuspecting cardholder. The relay introduces a communications delay, and this is what the relay resistance protocol detects. The secure channel also provides privacy protection. One of the important security objectives of Kernel 8 is to meet the requirements of the GDPR, the European General Data Protection Regulation, in terms of protection of PII, personally identifiable information. Hence, the secure channel also allows the encryption of card data sent from card to terminal, and goes further by allowing encryption of the card public key and its certificate so as to prevent tracking and transaction linking by a passive eavesdropper. As shown by the diagram, This is especially relevant for contactless transactions because although the consumer device must be close to the merchant's reader, an eavesdropper can be much further away. I'll now provide you with a pictorial explanation of how blinded DiffieHellman works. As a preliminary, I'm sure you will recall that with ordinary DiffieHellman, two parties are able to establish a shared secret simply by exchanging their public keys. The public keys can both be ephemeral or both be fixed, static, possibly certified. Or they can be a mixture with one static and the other ephemeral, and this is essentially the case with EMV. So in this illustration of blinding DiffieHellman, we begin with the card on the left having a certified public key pair, and the terminal on the right has nothing. At the beginning of the transaction, the card multiplies its public key by a 32-byte random number, the so-called blind, and the terminal generates a random ephemeral key pair. They then perform DiffieHellman to establish a shared secret. Actually, it's an x-coordinate of a point on an elliptic curve from which they derive AES session keys, one for integrity and one for encryption, thereby providing for a secure channel for exchanging data between card and terminal. The important thing is that the card public key provided to the terminal is the blinded version of the card's certified public key. So some of you may have noticed that so far there is no way for the terminal to actually authenticate the card, as all it got from the card was a randomized public key that looked like an ephemeral public key. And that's the trick for blinded DiffieHellman. Once the secure channel is up and running, the card provides the public key certificates to the terminal so that the terminal can traverse the PKI in the usual way, but the card also provides the value of the random blinding number, thereby enabling the terminal to check that the randomized public key it received at the outset is indeed the card's certified public key multiplied by the random blinding number. Note that this way the card does not generate digital signatures, and neither the card account number nor the card public key are sent in the clear, and this prevents unwanted tracking by potential passive eavesdroppers. I think this is a beautifully efficient protocol and very easy, especially if there would be a Java card API to help. We now move deeper into the security and the cryptographic processes defined for Kernel 8. The left half of this slide highlights the security features of the C8 specification, but what I want to focus on is the flow diagram on the right. Stepping back, we can think of EMV as providing two-factor authentication, something you are or know in combination with something you have. The flow diagram on the right deals with the second factor, something you have. The first thing to mention is that the white boxes represent data or information, whereas the blue boxes represent functions. Then we see that the left blue box is the blinded DiffieHellman key agreement for establishing the encryption session key used for privacy and the macking session key used for integrity and authentication. Next, I draw your attention to the top white boxes. First, we have the card static data that is hashed by the terminal and used when processing the card public key certificate, but that is also fed into a MAC calculation along with the dynamic transaction data. This MAC is called the IAD MAC. The IAD MAC is central in many ways. It is fed into the EDA MAC, which provides for the local authentication, but it can also optionally be fed into the card online application cryptogram calculation, thereby providing the issuer with integrity assurance of all the local transaction data rather than only a small subset of it. So this means that if the data has been tampered with, then the application cryptogram verification will fail. In other words, remote authentication is then able to protect against any fraudulent manipulation of the local data exchange, and especially attacks that try to subvert the relay resistance protocol. I will now conclude my presentation with 3 slides that deal in more detail with blinded DiffieHellman, session key derivation, and finally the 2 MAC calculations. So this slide shows again the blinded DiffieHellman protocol according to ISO 11770-3, but instantiated as in kernel 8 using elliptic curve cryptography. As previously explained, the special version of DiffieHellman used here is blinded, meaning that the card public key shared with the terminal is not the certified public key, but the certified public key multiplied by a one-time random number R, the so-called blinding factor. This, in some sense, makes the card public key shared with the terminal like an ephemeral public key, and thereby the key agreement is ephemeral rather than static ephemeral. However, to achieve card public key authentication, the card provides to the terminal inside the established secure channel the blinding factor and the public key certificate, thereby enabling the terminal to validate that the blinded key received in the first step of the protocol is indeed the product of the certified card public key and the blinding factor. As already noted, this method is very efficient and avoids the card having to generate digital signatures. But as you can see, inside the red circle, there is a choice about how the card calculates the shared secret Z using scalar multiplications. We will explore this further in the second part of this webinar. I will now move on to explain how session keys are derived. In EMV kernel 8, the session key derivation is quite simple, albeit it is based on the more complex, flexible, and generic methods defined in ISO 11770-6 and NIST SP 800-108. Accordingly, key derivation starts by extracting a derivation key, KD, from the blinded DiffieHellman shared secret. Each kernel 8 session key is then derived by applying AES with the derivation key KD to derivation data, where the derivation data varies depending on whether the derived session key is to be used for encryption or authentication. This functionality is already included in the standard JavaCard API and is described in more detail in the JavaCard forum part of this webinar. So this is my final slide, and with this I want to briefly explain the tweak applied to CMAC for calculating the IAD MAC. But first I'll explain what's shown on the slide. The top diagram shows the final block of the calculation of the local cryptogram that is verified by the terminal as part of local authentication. We refer to this MAC as EDA MAC. Input to the EDA MAC calculation is the application cryptogram and the IAD MAC. The lower diagram shows the final block of the calculation of the IAD MAC. The kernel 8 secure channel uses the CMAC function, which is already supported by the JavaCard API, to create these 2 MACs. Except, as you can see in the lower diagram, the CMAC function used for the IAD MAC has been adjusted by including a feed forward on the last block, so as to provide an element of irreversibility. We denote the adjusted CMAC function as CMAC plus. The reason for the adjustment is that we want to protect against an attacker manipulating the message without changing the value of the MAC. But CMAC is a MAC function, and this is what MAC functions are designed to do, I hear you say. Indeed, CMAC is by design non-malleable, but this is under the assumption that the CMAC key is not known to an attacker. However, in EMV kernel 8, we want to protect against the possibility of a man-in-the-middle attack, wherein during a payment transaction, a man in the middle is able to establish session keys separately with the card and with the terminal. This scenario might be possible if local authentication is skipped, for example. In this case, were it not for the irreversibility, the man in the middle might, in real time, be able to ensure that the IAD MAC provided to the terminal is the same as that produced by the card. They would do this by working backwards from the right to the left, decrypting a 16-byte padded version of the desired IAD MAC, and then suitably manipulating the message blocks. I won't say any more about this now, but hopefully this has given you at least some insight into the rationale for the CMAC Plus design. So to wrap up my part of the presentation, I'll call out the card side interests of the new EMV cryptography as follows. For contact EMV, there is the Schnorr digital signature as used by XDA, and for contactless EMV, there is blinded DiffieHellman and especially the card scalar multiplication and CMAC Plus. These can already be implemented on cards using manual calculations, but having them supported by the Java Card API standard will facilitate adoption by allowing much easier, more efficient implementation, standard evaluation, and performance improvement. I would now like to hand over to my colleague from the Java Card forum, who will explain how this works from a Java Card API perspective.
Thank you, Mike. My name is Pham. I'm a member of the Java Card forum. On behalf, I would like to show how the Java Card technology will enable a secure and efficient EMVCo kernel 8 transaction. Next slide, please. This is the copyright statement, so next slide, please. So first, I would like to show how a blinded DiffieHellman can be achieved with the existing Java Card version 3.2. As mentioned, shared secret is calculated by R multiplied with static key multiplied with the reader public key. R is the blinding factor, D is the card private key. One can compute twice the key agreement or scalar multiplication. With the first one, we can compute, for example, DC multiplied with the reader public key. And then the result, one can multiply again with the blinding factor. So we need two instances of a key agreement class with plane X and Y. In the next figures, I would like to show the performance measured on a PC. If we do the scalar multiplication, DC multiplied with the public key, it will take around 4.9 milliseconds. If we do the normal long integer multiplication, R multiplied by DC, it will take a roughly 0.05 millisecond. So it means it's about 100 times lower. The scalar multiplication is 100 times lower. What does it mean in terms of blinded DiffieHellman? If we compute completely, first 2 times scalar multiplication, then it will be in a range of 9.8 milliseconds. If we do first the long integer multiplication, then the scalar multiplication, it will take roughly 5 milliseconds. So we will, therefore, Java Card forum decided to make a proposal how we can achieve blinded DiffieHellman in a more efficient and a secure manner. Next slide, please. So the proposal is like usual in Java Card, we have a get instance method, factory, where you get an instance of the blinded DiffieHellman, where we feed in an algorithm. Currently only one is defined. This is alg ECDH EMVCo book E11. And external access is to define if the instance can be accessed via shareable interface or not. The next method would be get algorithm, as already known in the standard Java card, will return the algorithm, so the constant of alg EC BD EMVCo book E11. There's also one init method to initialize the instance with the static private key. Next slide, please. And three methods to retrieve the return size of each return method. So get blinding factor size returns the blinding factor size in bytes. Get blinded public key size returns blinded public key in bytes, and get shared secret size will return the number of bytes for the shared secret. So currently, if you're using P256 curve, all of them are fixed. Get blinding factor size is 32 bytes. Get blinded public key size will be 65 bytes, and get shared secret is 32 bytes. Next slide, please. We have then the method to generate the shared secret. It will take other public data. This is the card terminal public key with offset and length. And then three output parameters is one is for the shared secret, one is for the blinded public key, and one is for the blinding factor. All of them will be written back in plain. And now a platform can do an efficient, optimized calculation of blinded DiffieHellman. We have a next slide, please. There's a second general shared secret method. Same first three parameters again for the public card key. And then we have one is for shared secret. It's now written into a secret key object. And blinded public key is already in plain again. And also blinding factor can be written into a secret key. This is to provide a more enhanced security API if someone wants to get the shared secret not in plain, but in a platform-specific mass manner. Next slide, please. So this is how a pseudocode may look like to calculate a blinded ECDH on a Java card. According to Oracle best practice, one should create all applet instances or buffers during installation or personalization. So the first 4 lines is how to create a private key. Next is to create the key agreement instance, and then we have to initialize the private key during personalization. Next would be this ECDH.init to initialize the key agreement instance. This will be done once in the card lifetime, and on an operational phase where we would like to do the payment transaction, applet has to call ECDH generate shared secret. And now here I choose the one with the plain. So we receive the data from card terminal. We have to feed in as a other public key, and then 3 buffers to return back the shared secret, blinded public key, and the blinding factor. Later on, how we will do the key deviation will come in the next 2 slides. In the next slides. Next slide, please. For the blinded ECDH, we're also offering this one-shot as defined in the Java 305 already. And it's also best practice I mentioned in the TCA, Trusted Connectivity Alliance, stepping stones for Java applet developers. Whenever it's possible, there's a recommendation to use the one-shot to reduce number of NVM writes. How does it look like is an example code. First, we open a one-shot with the parameters EMVCo. Then we initialize the one-shot object with the private key, and then calling generate shared secret to get the 3 output parameters back. In the finally close, we have to close it again and release the one-shot resource. Next slide, please. So after the blinded DiffieHellman, we will have a shared secret. This is the X coordinate will be used to derive the KD keys. This is done via AES-CMAC with V as 16 bytes of zeros. And this Java card already have existing API. This is the signature class with the constant alg underscore AES underscore CMAC underscore 128. With that one, KD will be derived. And then we will have the 2 session keys. One is for encryption, one is for integrity. With the constant data as an input will be encrypt with the KD keys. And there we also have a standard JavaCat API already available. This is the cipher.alg underscore AES underscore block underscore 128 ECB nopad is already available. Next slide, please. So to support additional AES-CMAC and easy SDSA Schnorr signature, there's already a standardized API that has been defined 25 years ago, and it's still suitable for the additional algorithm like AES-CMAC plus. We only need to add one more constant. This is 6 cipher CMAC plus EMVCo E11. And for the Schnorr signature, there are 4 types with the normal that is not used by EMV, but we will introduce this as well, a proposal. One is the normal no verify, means to have possibility for the platform to reduce the footprint, just implementing the sign operation. And then we have the 2 constants for optimized. This is used by EMVCo, where only the X coordinate is needed to calculate the signature. And here we also have these 2 constants. One is optimize with sign and verify, and one is no verify for footprint optimization. So now I'm done with my presentation. Next slide, please.
Thank you, Hui and Mike, for this presentation, and I think a very extensive review of the old, new, and future cryptography for EMVCo. We can now open the mic for questions from the attendants. Do we have any question? You can just unmute your microphone and ask directly the question to Mike and Hui.
Hello, can you hear me?
Yes.
Thank you for your presentation. I have a short question regarding the proposed API for the ECDH. And the question is that, is my understanding correct that the first location which the applet can obtain the blinded public key is after generate secret?
Yes, it is.
Okay, and so please correct me if I'm wrong. Is it true that the terminal need the public key of the card in response to the get data commands after generate processing after the GPO command? I mean by this proposed API, it seems that the card should already have the public key of the terminal in order to generate its public key blinding factor and blinding public key. But if I was not wrong, the terminal needs beforehand the public key of the card.
Sorry, this is Mike Ward. I think, if I remember right, that the terminal goes first in the protocol, and so the card will have that data.
Okay, so isn't it incorrect that the terminal first fetches the public key of the card?
As I remember in the GPO command, the terminal will send his public key to the card. And on that
Okay.
response, he will respond back and the blinded public key that both can do shared secret calculation and establishing the secure channel. And later on,
So
it will share the blinding factor.
Okay. Thank you. Got it.
Thank you. Any other questions, please?
Yeah. Hi, Paul speaking from Jainet Secure. It's actually linked to exactly the same thing, just to continue the process. So we have the authentication happening after generating the keys. And you're saying that the blinded factor is given after in a following command in the process of the transaction?
Yes, inside the secure channel.
All right. Okay. And for the security level, do we have the same thing, like level 1, 2, 3? Should we be we're enciphered, right? After establishing this secure channel.
Okay. There are two aspects of this, I suppose. One is the original version of Blinded DiffieHellman, where everything is sent inside a secure channel after it's been established. But then in kernel 8, there is, should we say, the more optimized, the lean mean version of the protocol, where only data that needs to be sent inside the secure channel or encrypted is. So from what I remember, actually, the blinding factor is sent in the secure channel. But for example, the issuer public key certificates, the issuer public key certificate, singular, is not encrypted. It doesn't need to be.
Correct. Yeah. Okay.
So it's a selective process.
All right. Perfect. Thank you very much for your answer.
Okay.
Yeah. Good morning. This is sorry.
No, go ahead. Go ahead.
Yeah. Good morning. This is Ram from Toshiba. So I have a question regarding basically two questions. So as per the Java card API which is proposed, so it is that the card platform has to generate the blinding factor. So the application need not generate. It will be the card platform which will generate the blinding factor and then do the blinding of the public key and then send the response in the API as the blinded public key and the blinding factor. Is that correct?
Yes, the platform will generate the blinding factor and also compute the blinded public key and the shared secret. And this can be retrieved either by a byte buffer or within a key. Yes. And then applet has to send it out by himself.
Yeah, okay. So what was the thinking behind that the card platform has to generate? So already there is a API for generating, say, random number. So why is that the platform has to generate? Is it for the optimization?
Yes, it's mainly for optimization.
Okay. And so, so this very optimistic question. So when can we expect these APIs to be part of the Java card?
Okay, maybe I can take this one. This is Jean-Daniel Rossel from the JavaCard Forum. So from a
Yeah.
JavaCard Forum perspective,
Yeah.
the API I think is pretty much ready, and
Okay.
there has been discussions, and I would say we reached some kind of agreement that this would fit the EMVCo requirements. Now, as you know, in the process, we are in the process of recommending this to the owner of the JavaCard specification, which is Oracle.
Okay.
Hopefully, we'll have managed to have some agreement from acceptation
Okay.
of this recommendation. If yes, then it would be part of the JavaCard specification. If not, then we would find a way to issue the specification.
Okay. Thank you so much for the answers. Thank you.
You're welcome.
Sorry, may
Hi.
I add something to the?
Yes, please.
I wanted to add something to the answer to the previous question. What is the reason why the blinding factor generation is put on the shoulder of the platform instead of the applet? And I think one of the reasons, or maybe the actual reason, is that for crypto implementations, it's always the case that they design it in a way to reduce the chance of invalid usage. So for example, you have for the ECDH API no way, or at least no normal way to set the ephemeral key generated, and it's the responsibility of the platform itself to generate this key. And for this proposed API, it should be also the case that there is no reason for the applet to generate this blinding factor, because if the applet developer is the responsible person to set this value, then in a bad implementation, he may feed this with a fixed value or something like that. So they put this on the shoulder of the platform.
Okay. Yeah. It's clear. Thank you so much.
Sure. Thank you.
Good morning. One question to Mike. Did I understand right that the local authentication is different for contactless interface and contact-based interface?
Yes, with the new cryptography, the contact interface and contact kernel is described in EMV Book 2, version 4.4, and that includes where the card creates a digital signature called XDA, in the same way as that happens with today's cards, where they might create a DDA or CDA signature. However, for contactless, it's different, and that's where we have the blinded DiffieHellman secure channel.
So what is the rationale? Why is this different techniques on both the interfaces?
Well, it's historical, to be honest. Originally, so if we look back 10 years ago, the plan had been to have the same on both interfaces. That was a project which was eventually canned, but we then, in EMVCo, we introduced first a contact solution and then a contactless. And the idea was to try, certainly for the contact, to try and be as similar to what's done today as possible. Hence, use a digital signature from the card rather than any new secure channel. But when it came to contactless, because contactless benefits far more, for example, with the privacy aspects, it was absolutely decided to go with the secure channel for that. So that's the history behind it. I know it may appear somewhat strange.
Thank you so much.
Okay.
So there is one. Sorry, I have one question. Could you hear me?
Yeah, sure.
One question about the API. Actually, there is the possibility to output the shared secret in a key object, if I'm correct. And but anyway, the shared secret shall be then the input to the CMAC in order to derive the derivation key, the KD. So I think that there is a need in whole case to put the shared secret in a byte array, isn't it?
So there is in Java Card 3.1 and 3.2, there's a new KDF, key deviation class. Here you may need the shared secret if you would like to enhance security from a side channel leakage, so that the platform can already store shared secret not in plain but in a platform specific secured manner. And the next step would be maybe in next version we can use the key deviation class to derive the two keys.
Okay, thank you.
Another question would be, is EMVCo preparing for PQC cryptography also?
I think that's probably a question for me. Yes, well, we're certainly watching the whole area of development of PQC, so that's quantum resistant cryptography. And in fact, we believe that Kernel 8 is crypto agile and can be added to in the future if need be. And indeed, the SWG is monitoring and can support standards development of quantum resistant solutions in order to steer a path to maintain EMV as fit for purpose in the future. But it has to be a cost-effective solution, and whose implementation timeline is commensurate with the quantum threat being realized, certainly 10 years distant, and by our projections, and I think by popular projections, unlikely before 2040. So whilst we are monitoring the developments around quantum computing, we don't see any immediate concerns, especially as EMV payments are more about real-time authentication rather than dealing with the threats of harvest now, decrypt later. Having said that, we have developed a position statement for the EMVCo associates, and we hope actually to make this publicly available very soon. Okay.
Thank you.
Maybe one question on my side. So Guillaume Dabozul from Carte Bancaire. Mike, could you explain again the rationale behind the need for this EMVCo dedicated CMAC that you called CMAC Plus? And can you tell us if it was already specified in Book E?
I believe it is specified in Book E. In answer to that question, I believe it is specified in Book E. And albeit as a design feature, it came to C8 maybe slightly later in the evolution than the other features. But the main reason, just to maybe rephrase my explanation earlier, was the role of IAD MAC is not just as part of the local authentication, it's also as part of the remote authentication, insofar as it can be fed into the calculation of the issuer's application cryptogram. And to that end, you have to ask yourself the question, well, what if the local authentication hasn't happened? Maybe the issuer decides not to implement local authentication using certificates on the card. So then what happens to the online authentication? And the purpose of CMAC Plus is to make sure that even if the local authentication with certificates does not happen, the online benefit of the IAD MAC being fed into the application cryptogram is still good. And so in particular, you have to defend against the possibility of a man in the middle, because you can't rely upon the certificates. You have to defend against the possibility of a man in the middle that can establish session keys with both the card and then with the terminal. And in order to prevent them subverting the IAD MAC calculation and manipulating the messages between the card and the terminal, you need this element of irreversibility to ensure that it's not possible to do that. Does that kind of make sense?
A little bit complicated to understand, but maybe in the last release there are some more details. But what is
Yes.
a little bit surprising for me is when you say, look, when local authentication is not performed. For me, it is mandatory to make this local authentication mandatory. So,
well, the
but
local authentication processes are mandatory within kernel 8, but having certificates is not mandatory. And so it's possible if a card would purely rely on remote authentication and not have certificates, then you could, in theory, have a man in the middle between the card and the terminal. Yeah.
Okay. Thank you, Mike.
So that, yep. Okay, my pleasure. And by the way, I'm showing slide 30 now because I saw in the chat there was a request to see slide 30 again.
Thank you. And remember, the presentation will be available soon also. Do we have any more questions? Yeah, I would have a last one. We had very detailed question and very deep question about the protocol, but on a more generic level, what's the status of this kernel? When would we expect to have this rolling out?
Well, we talk about kernel 8. Well, that has already been published last year.
No, I mean the one with the latest cryptography that we've seen this morning.
Yes, that was published last year, and we already have the testing and approval processes in place for it, and we indeed already have kernels qualified and approved. And you can go to the EMVCo website to see the list of approved kernels.
And from your perspective, how critical is the availability of the API? Is it something that you think will need immediate attention, or we still have a few months in front of us?
It's not critical insofar as the world can get by without it, but it certainly would make performance and implementation a lot simpler once we have the API.
Okay, understood. So it's a 9:59 and probably time to wrap up. Thank you, Mike, and thank you, Yui, for your presentation, and thanks to the audience. I think very a lot of interest and very interesting questions. You will find, as I say, the presentation on the website. We have a replay this afternoon at 5 p.m. Central European time for the other time zone. If you have colleagues that would like to attend and if you want to recommend, so there's still time for them to join. There's also 2 other webinars for the 2024 series. If you are not registered, please look on our website and feel free to register. And also we have a lot of interesting presentations from the previous years in the YouTube channel. So if you have time to use during the holiday season, just browse the different content of the channel. With this, thank you everyone, and hope to see you soon. Goodbye.
Thank you. Goodbye. Thank you very much.
Thank you. Goodbye.
Cheers, Mark.